Hello everyone, this is Dr. Ali, and in this session we want to continue our conversation with the how to do this, how to code this knapsack problem. So we come to this point that how to formulate this knapsack problem in the minimization form, either method 1 or method 2 here. Now let's see how we can actually implement this knapsack problem using one framework. There's a one Python framework that I'm using. It's called Sci-Fi, and there is a module under it, optimize differential evolution. Um, and this differential evolution, you can read it and see what are the parameters they need. And if you look at the first parameter here, it's font. Okay, and what is the font? Let's read through this and we'll see what is this about. It says the objective function to be minimized. So I hope this is now clear that why I wanted to turn the form of the maximization form that we had into the minimization form. See, that's why I turned this to the minimization, because I told you this is only for the sake of the framework I'm using. Because this framework, it requires me an objective function to be minimized. So, and it says must be in form X and star args, right? Where the X is the argument in terms of a 1D array, and the args is a tuple of any additional fixed parameter needed to be completely specify the function. All right, and the N is the len X, obviously. Okay. So basically, this X is that sequence that I was talking, that we need to select a sequence in order to maximize or to minimize the value of those items that we didn't pick. And the bounds here, the bounds are basically says for each one of those values that we have, for each one of those xi, what is the range of those xi's? So of course, for us, the minimum value for xi is 0, the maximum value is 1. And this, for our scenario, the xi's are binary, but here you expect some real data. So when we say 0 and 1, it will create like a real data and floating data between 0 and 1. But then we can do some parsing after that to just turn into the either 0 or 1. So we can do the round function to just round it. And then, yeah, it says defining the finite lower and upper bounds for the optimizing arguments of func. So this bounds is showing the bound for each one of those parameters, or each one of those binaries, or the xi's that we pass for the argument as f. And the rest, you can read it on your own. And these are the most important thing. But remember, I don't get into detail of what is this financial, what is this differential evolution is, and how this evolution algorithm works. There are lots of different algorithms. This is just, I'm assuming that you guys know already, but maybe later on I create a bunch of videos on what are these evolutionary algorithms are, and what are the differences. And because if I want to explain what is this pop size is, what is this mutation is, it takes a lots of time. So we cannot record it in this video. So by having said that, let's see. Yeah, let's start coding. And actually, I coded this already, and I just walk you through it so you'll see that what are the steps. So first of all, what I did here, I imported some modules, right? And if you see here, this is the module that I already told you, differential evaluation of this package, sci-fi that optimize. Okay, so this is already I imported. Then this is the function that actually is the function that this evolutionary differential evolution requires us to pass, the function that I already explained. So I called it knapsack value. Knapsack value, it expects us to passing x and star args. So these are the star args that I put it in the form of parameters here, the rates, values, and maximum weight. Okay. So the end goal is finding this x, which is a sequence, which is saying that either pick this item or not pick this item. Okay. And now this total weight. So what is this total? Let me put this next to each other. So you see, all right, what is this total weight? This is this part. Actually, this part. This is wi xi, right? So np dot weight times x, which says what are the weights of those items that we pick. And then he says here total value. What is this? Is this objective function vi times xi, okay? And now I also pick the total value that not selected. Actually, I think I started with this part first. So total value that not selected. Basically, this line 5 we calculate in this term here. This term that vi times 1 minus xi. V or values times 1 minus x. And then the alpha here I put it at 1000. Remember I said this is a coefficient that we need to modify. So here I just pick 1000. You can just play around and pick different values. How we can pick the right value for alpha, it has its own set of discussion, and how there are some algorithms developed for only picking this alpha. But for the sake of simplicity here, I just pick 1000. And why I pick 1000? I tried different numbers, and I see this 1000 it works for this problem. So now we say if there is a penalty, what does that mean? If the total weight, if those weights that we picked and put it in the knapsack is more than the maximum weight of the knapsack, then we need the penalty. What is the penalty? Alpha times total weight divide maximum weight minus 1. This is the penalty. Remember, alpha times, and we know that there is a penalty because total weight is more than maximum weight. So we already considered this. So you see total weight, this is a total weight, divide by max weight, which is W max, minus 1 times alpha, okay? But if it is not, it means total weight less than the capacity of the knapsack, then penalty is 0. Then we come here, this is just for sake of storing the intermediate result that is generated, because this is an iterative method. It's just iterating, and at each iteration it will generate a new sequence of x and evaluate. Okay, how good is this? If it is not good, just skip it. If it is good, generate new set of sequence based off the previous sequence that we already have. This is, and how they doing it is the whole concept of evolutionary algorithms are based on mutations and parent and the offspring and all of this, that how it will generate new set of sequence and then evaluate this new set of sequence, and he picked the best of those sequence and keep doing this iteration till it reached the point that we see that we reach the maximum possible iteration, or the maximum possible value for the goal that we are looking for. So here I just logging the intermediate values, and here we just say the cost equal the value of total value that of items that we didn't select plus penalty. Here, value of the items that we didn't select plus the penalty, and we just return it. And remember, this is a minimization. That's why I said we need to turn it to the minimize, because we know that this knapsack, we know that this framework is looking for a function to minimize. So then I give an example here. Let's say we have 10 different items with these weights, 5, 4, 6, and so on. And each one has different values. And the maximum weight for the knapsack is 10, the capacity. And we know the bounds for each item is either 0 or 1. Either we can pick it or not. So this is also in this form that this sci-fi needs for us. So, and then this part that I already explained, nothing. And then we call that that function, that optimized function that provide for us with sci-fi. We're passing the knapsack, which is the function that we want to minimize, this function. we pass that function and bounds and the arguments, and pop size and maximum iteration. If you don't get it, what is this pop size? These are the concepts coming with evolutionary algorithms. If you don't know them, just skip it. Just leave it as it is, or just don't even insert them, because the default values is good enough. So what you need to do is just pass in these three arguments, right? And then when when this algorithm done, it will return the result. What are those x that we reach? And then I just here it says, okay, what is the value that we reach, and what is the actual weight that we reach, and what is the sequence. So this is optimal solution, and the maximum optimal weight 120, and the optimal weight is 8. You see, the maximum that we had here for the actual weight of the knapsack was 10. So after running this algorithm, it gives us this sequence, and it tells us that we reached the maximum, the value, these values we picked, this one we picked. So, and the summation of their weight is 8, which is not beyond this 10. So no violation. And then if I run, let me run this real quick. Okay. And here is the actual all of those items that it's generated. So let me stop here, and in the next session I'll try to explain this chart, and we move to the next session. I hope this was informative for you guys. If you have any comments, leave it down below. Otherwise, see you next session.